A free body diagram is our standard tool for identifying and organizing the interactions that an object is experiencing at one particular moment in time. In this video, I'm going to show you the guidelines and conventions for drawing free body diagrams, and at the end, there'll be a couple of practice problems for you, so be ready for those. Here is the scenario we'll be examining. We've got this chimpanzee here pushing on a box of llamas across a rough surface. The box is also being pulled via this rope by this here pachyderm. We're going to focus on the box here, the box of llamas. We want to look at the interactions that the box is experiencing and diagram all those interactions. Note we're also told that all of them are accelerating to the right at this moment, and their velocity is to the right as well. Okay, guidelines. We model the motion of an object by considering it to be a free body, that is free to move in any direction. It's not fixed in space. So our diagram starts as follows. The object, which is usually standing in for the center of mass of a system, the box here is actually a system of zillions of atoms, but we're going to represent the box with a dot at the center of mass of the box. So here's the start of this free body diagram and every free body diagram. You can draw a box of llamas if you can draw a dot. You don't have to be a great artist. Every object is just represented as a dot when you're drawing the FBD for that object. 2. The FBD models the interactions that an object is experiencing at a single moment in time. This is a frozen moment in time. As soon as the interactions change, a new FBD must be drawn. 3. Here's where the real work starts. Count off all the things the object is interacting with at that one moment. This includes things the object is touching, such as other objects, surfaces, and media, typically the air, and also includes a long-range gravitational interaction with the Earth itself. An FBD commonly includes 0 to 6 significant interactions. At every moment, a macroscopic system actually experiences zillions of interactions between its atoms and the atoms in immediate contact with it, and every other atom in the universe through the long-range force of gravity, and it's impossible to keep track of every interaction. So we need a simplifying model. When modeling a set of interactions, we may compare their magnitudes and directions to make some simplifying approximations. Here those are. A. Treat zillions of tiny atom-to-atom forces in the same direction as a single big macroscopic force. So for instance, all the zillions of atoms in the surface here that are pushing up on all the zillions of atoms in the bottom layer of the box, we can represent those as one single upward force from the surface pushing on the box. B. Neglect forces that are very weak compared to other forces. This is often true of air drag on slow-moving objects and almost always true for gravitational interactions with anything other than the Earth. The mass of the elephant here is actually exerting a force of gravity on the box of llamas, pulling the box towards it, but that's a very weak force compared to the force of gravity from the whole planet Earth pulling downward on that box. So we ignore all forces of gravity except that from the Earth because they are weak compared to the force of gravity from the Earth. And C, neglect interactions that always cancel out, such as air pressure, which exerts very large forces but pushes equally on a stationary object in all directions. So those air pressure forces tend to cancel out, and we leave them off of our diagram. Okay, so let's get an inventory of the interactions, the significant interactions that this box of llamas is actually experiencing at this moment. I count 4. The box of llamas is interacting with the rope that it's touching directly right here through a force of tension. If there's a rope or a string or a cable pulling on something, we call that a force of tension. The chimp is pushing on the box to the right, so that's a contact force. This chimp is directly touching the box. The surface down here is also directly touching the box, pushing up on it, and there's also friction between the surface and the box. That's a contact force with the surface. And the fourth one is easy to miss, Earth. the planet Earth is pulling down on the box with a force of gravity. If we zoom out, you can imagine the box sitting on the entire planet here, and through the long-range, non-contact force of gravity, the entire mass of the Earth's interior is pulling downwards on the box. So we must include that interaction as well. Note that we do not have an interaction between the box and this pachyderm right here. The pachyderm is not directly touching the box. The rope is right there, and the pachyderm's holding the other end of the rope, so the rope is interacting with both the box and the pachyderm, but the box itself has no interaction with the pachyderm, only with these three things and the Earth itself. Okay, so there's our catalog of interactions for the box. Let's turn to the next guideline. 4. For each significant interaction, draw an arrow on your dot to represent the force exerted on the object. Forces on the object, on the box. Do not include forces your object may be exerting on other objects. So here, we're going to include all the forces on the box. We're not going to include the force that the box is exerting on the chimp. The box is pushing backwards on the chimp. The box is also pushing downward on the ground. We don't include those forces because those forces are acting on the chimp and on the ground. If we want the FBD for the box, we only want the forces exerted on the box, not forces exerted by the box. Okay, B. All those arrows we're going to draw, they should start at the dot and point away from the dot in the direction the object is being pushed or pulled. C. The length of each arrow represents the magnitude or strength of that force vector, and so it should be drawn in proportion to any other forces. D. Each arrow, each force vector, should be labeled, typically capital F with a harpoon over it and some subscript to tell us what type of force it is. So now let's put down a rough draft of this free body diagram for the box. We counted 4 interactions, so I've got 4 arrows to represent those 4 interactions. There are 4 force vectors. Here is that rope pulling up and to the right with a force of tension, T for tension. Here is the chimp pushing to the right, F sub A, as in the force from the ape. We could also say this is an applied force, so A is either for ape or for applied by the chimp pushing to the right. That's contact force. Fg, force of gravity straight down from the Earth. And then the surface must be pushing up on the box to hold it up, but note that it is a rough surface, indicating that there is friction present. So there is friction opposing anything that's trying to slide on the surface, and also friction provides traction for anything walking on this surface. So the surface is pushing up on the box, but also to the left on the box because of friction. The combination kind of points up and to the left. There's our force from the surface on the box. A common mistake here involves the force from the chimp. Some people would say that, well, the chimp is on the left, pushing on the box this way, so maybe you should draw that arrow pointing toward the dot. That's wrong by convention. We always draw all the arrows starting at the dot and pointing away. So the force from the chimp should go over here on the right side, pointing away to the right. Okay, so we've got our forces on here, but we do have to think about their proportions. To get the proportions correct, take all our force vectors and consider breaking them into components. Draw a set of xy axes over here on the right, and then for any forces that are not aligned with them, that is tension and the contact force from the surface here, break those forces into components by making them the hypotenuse of a right triangle, and the legs of the triangle are the components of that force. So here I've got ftx and fty, the x and y components of the tension force pulling up on the box. For the contact force from the surface, we actually have special names for the component that is perpendicular to the surface. We call that the normal force, the part of the surface pushing up perpendicular to the surface. And then the part of the contact force with the surface that's parallel to the surface, that's friction. We call that friction. So these two components have special names. We've got to make sure we drew all these components and forces with the right proportions. So we must go back to this scenario and recognize that our diagram has to capture this piece of information, that the box is accelerating to the right. Let's consider the x and y components of the forces. If we're accelerating to the right, that means that the net force in the x direction must be to the right. Looking at our diagram, I've got a force to the right here, tension's pulling to the right, the chimp is pushing to the right, and friction is pushing to the left. So if our net force must be to the right, that means this tension component and this applied force from the chimp must be greater. The sum of these has to be greater than our force of friction. So the way we drew it looks like they already are. That part of our diagram, that aspect of our diagram is good. The rope FTX plus the chimp's force, those have to sum to be greater than the force of friction. Looks like we're all good there. Now let's check the y direction. In the y direction, our acceleration is 0. The box is not floating straight up into the air and it's not sinking down into the ground. The acceleration in the y direction is 0. Therefore, the net force in the y direction must be 0. The forces are balanced in the y direction. Checking our diagram, I see that we have a normal force in the y direction, the part of this contact force with the surface pointing straight up. We also have part of the tension here, Fty, pulling straight up, and those are competing with the force of gravity here, pulling straight down. So it must be that this normal force plus the y component of tension, those have to be exactly equal to, when we add them, exactly equal to the force of gravity, exactly balancing gravity, as I've stated here. The Fcy and Fty, the sum of those has to be exactly equal to gravity. So we have to make sure we draw the diagram so that that looks like it's the case. All right, I think we're ready to kind of do a second draft here, rescaling those components. And, maybe one more thing to note. I doubt very much that the chimp here is pushing as hard as the elephant is pulling. So maybe I shouldn't draw this applied force from the chimp quite as big as the tension that's ultimately coming from the elephant. Okay, second draft for that free body diagram for the box. Here, I've shrunk down that force from the chimp to make it smaller. That's more realistic. And I've highlighted the forces and components that we should be comparing. Here, the FTX from the tension and from the chimp, the sum of those now is clearly bigger than that force of friction. So we will get a net force to the right and acceleration to the right. In the y direction, I've highlighted in yellow the normal force here, that y component of the contact force with the surface, and the Fty here, the sum of those looks like it's about equal to our force of gravity right there. This plus this is about the same size as that. So to finish the free body diagram, we just have to kind of clean it up a bit. By convention, we don't always show all these components. So our final FBD for the box, we obtain by erasing the components and showing just the forces. However, there's an exception. With a contact force from a surface, you actually draw in the two components separately as if they were two separate forces. So we're going to replace this component with something that looks like it's its own force, a normal force, F sub n, and replace this component here, the part parallel to the surface, that friction, with its own force, F. So here's our final FBD for the box. There's the tension, there's the force from the chimp, here's gravity pulling down, here's what we call the normal force, the contact force from the surface pointing perpendicular to the surface, and here's the force of friction, part of the contact force of the surface parallel to the surface. These are really just two components of the contact force, but we always draw them if they are two separate forces of their own. Okay, that covers the FBD for the chimp. So I've got one last guideline to point out, 5 here. I'm sorry, that was the FBD for the box. One final guideline here, velocity is not an interaction. A velocity vector for an object is not included on an FBD. So where's my original scenario? Here. The box is moving to the right at the moment, but we do not include that velocity on our FBD anywhere. The object may be moving. That's okay, but we must be clear that velocity is not a force. And so the object's velocity vector is not included on the FBD. The object may be moving because it interacted with something in the past, i.e. because something pushed it a moment ago, in which case the movement, its velocity, is the result of an interaction. But if the object is not in contact at this very moment with the thing that pushed it, then there is no interaction at this moment, and there should be no pushing force on the FBD. An FBD only represents interactions, and only interactions that are occurring at this very instant. That's the final guideline, and so I have a couple practice problems for you. I would like you to diagram the interactions that the chimp is experiencing. Let's get an FBD for the chimp. So start with a little inventory here. Count out what are the objects that the chimp is interacting with and what type of interaction is each one. Pause the video and make that list. Ready? Here's what I see. 3 interactions. The chimp is interacting with the box that it's pushing on, the surface that it's touching, and of course the whole planet Earth that's pulling down on our chimp right here. 2 contact forces and a force of gravity. Now use that to draw the free body diagram for the chimp. Pause the video, draw your FBD for the chimp. Ready? Here's my draft free body diagram for the chimp. I've got the force of gravity from the Earth pulling straight down. I've got the box pushing to the left on the chimp. If the chimp's pushing on the box, then the box must be pushing back on the chimp. And then the contact force from the surface here. Surface is pushing up on the chimp, but the surface must also be pushing forward on the chimp. The chimp is accelerating to the right as well as the box. So if there's an acceleration to the right, something must be pushing the chimp to the right. That's the traction right here between the chimp's foot and the surface. Friction pushes to the right, that's our traction, allowing the chimp to walk forward and accelerate forward. So our surface ultimately pushes up and to the right on the chimp, so there's our surface contact force. The rightward part, that traction, that we call our force of friction, and that upward component that we call the normal force. So redraw your free body diagram. If you need to, make any corrections and clean it up and to draw a final FBD without unnecessary components showing. Pause the video, draw your final FBD for the chimp. Ready? Here it is, now showing that contact force from the surface broken up into these 2 components, which are represented as if they were individual forces, the normal force and the force of friction. Here also, I've got a little tick mark on the normal force and the force of gravity, indicating that they are exactly balancing each other, exactly the same size. All right, one more test case for you. How about, can you draw a free body diagram for that pachyderm right there? Start by cataloging the interactions it's experiencing. Pause the video, write down all the interactions that all the objects the pachyderm is interacting with at this moment. Ready? I count 3 objects the pachyderm is interacting with: the rope that it's touching, the surface that's touching, and the planet Earth pulling down on it. The pachyderm is not directly interacting with the box. So there's that tension pulling this way on the pachyderm, the contact force from the surface, and our force of gravity. Now draw a free body diagram for the pachyderm. Pause the video. Ready? Here's my draft FBD for the pachyderm. Contact force from the surface pushing up and to the right. Force of gravity from the Earth pulling straight down, and our tension from the rope pulling down and to the left. Once we clean that up, our final FBD, pause the video, clean it up, adjust yours. Ready? Final FBD for the pachyderm.